Section 12.2, exponential functions. What is exponential functions? The functions that we have had so far, they all have base as a variable and power was the number, like y equal x2, y equal x3, y equal x5. Their bases, all the bases was variables, but the numbers or exponent were the numbers. Exponential functions is different. The base is the number and the power is the variable. So what it is here, like if x is a positive number, y is always positive. But even if x is a negative number, like -1, what is 2 to the power of -1? 2 to the power of -1 is not -2, is 1/2, which is 0.5. Or let's say x is -3. Y is 2 to the power of -3 is 1/2 to the power of 3 is 1/8. See, in any case, y is always positive. Whether x is positive or negative, y is positive. Again, exponential function is a type of function that power is a variable. Now, some examples here. This one, 2 to the x. So what we do, we just take some numbers and plug in, see whether x is 0, positive or negative, y is always positive. Since the y is positive, the graph is always above x-axis. This is all the positive y's are here. See, that's the shape of the graph. Most of the graph in this chapter, they all kind of look very similar. They all are above x-axis when by plugging the numbers. Look at this example. Y is half to the power of x. Again, remember here we are just putting some positive or negative numbers, and y is always positive. So when I look at the picture of this one, you see, this is y equal 2x that we had. This is y equal half to the power of x. They all are above x's because y is always positive here. See, the y-axis. If the value of number, if the number which is the power, the base, y equal a to the power of x, if the base, this a is greater than 1, like 2 to the power of x, 3 to the power of x, 5 to the power of x, that's how the graph looks like. If a is between 1 and 0, means it's less, then the graph going in this direction. And you could figure this out by plugging numbers. So any type of exponential function, see all these exponential function, the power have x in it, base is a number. So if you put any number, positive or negative, you see the y is always positive. So what's the graph of 2 to the power of x minus 2? Or 2 to the power of x, they all are similar. Two to the power of x minus 2, 2 to the power of x, 2 to the power of x minus 2. See? Now, sometimes you have x equal 2 to the power of y. In that case, you should always start with y. It means you put some numbers for y first, you plug in, and then you find the x. So you start with these numbers first. So the only difference is now the graph would go below x-axis like that. See? This is 2 to the power of x. And what is inverse of this? Remember, to find the inverse function, you draw the bisector, which is y to the x. Image of this 2 to the power of x with respect to this line is that, which is the inverse functions. So now based on all this, then we have the homework problems. They all are graph. Like here, 3 to power of x, we want you to tell which one of this is the correct answers. You need to graph 3 to power of x plus 3 and tell which one is correct. One way is if you already have the answer, you have the pictures, you could actually take some numbers and plug in to see if it will work. Or you could just graph it. Let me show you how you graph it. There were 9 problems here. And this is how I graph. So all I do is just put a few numbers. Like I put 0 here. What is 3 to power of 0? Any number to power of 0 is always 1. I put 1, 3 to power of 1 is 3. I put 2, 3 to power of 2 is 9. When you put a negative number as a power, is always a fraction, 1 over 3, which is a small number. Or when you put negative 2, then it's 1 over 9. Same thing here. So for all of them, remember, I use 0, positive, and negative numbers. And you notice y is always positive. This is the difference here, because there is a negative 2 here. Like when I put 0 for x, what is 5 to power of 0? 1. But then 1 minus 2 is negative 1. So y is negative. It just depends on if you have something in addition to the x next to it. What if x is 1? 5 to power of 1 is 5. 5 minus 2 is 3, and so on. Again, this is the case. All y's are positive. When a, or the base, when the base is less than 1, remember, the graph would be like this. This is in case base, which is 5, is greater than 1. Now, and this is a case that your first variable is y. Well, what you could do is the first column, it could be y. You start with y, you put some numbers for the y, and then you find the x. So you could look at all this graph. See again, this one is 5 to power of y. When you draw the table, start plugging number for at y first. Then you find the x. This problem has 2 different problems. One is 4 to power of x, one is 4 to power of y. So you see there are 2 graphs, 4 to power of x. So I start putting some numbers for x. Here, some numbers for y. There was one also problem, which is mostly see in economic, is this formula. This formula is given in the problems, okay? So first they are saying that, and they're saying here, t is the number of years, and VT is $1 a month. So let's say if I put t equals 0, if I want to graph this, t equals 0, you put 0 here, 0.8 to power of 0 is 1, so it's 54.1. You put 6, you calculate whatever that number is, you do all this, and you put these numbers here. And that's how you came up with this graph. So one of them I can show you, like this one is 0.8 to power of 3. So here it's 0.8. It depends what kind of calculator you're using. To power of 3 times 54.1 27.7. So this is like a 27.7. See, it's a very large number. So you could do it also for the other ones. And one thing is, because number of years and both variables are dollar and number of years, they cannot be negative. That's why your function is in the first quadrant, because in the first quadrant, everything is positive. X is positive, Y is positive, okay? So T and Y have to be positive. You can't go beyond the first quadrant on this one.